Hi, I'm Jared Bodiger, Education Services Manager for Deskcase Corporation, and this is Precision Lubrication for Electric Motors. So what is precision lubrication? Well, precision lubrication is not about using better lubricants. In fact, if you take the average machine and remove the average lubricant from it and replace it with the best lubricant money can buy, in most cases you won't improve much. Not to say lubricant quality isn't important, but in order to get value from quality lubricants, we have to do some other things right first. Something else that isn't precision lubrication is just doing more of it. Lubricating things more often than is necessary is not only a waste of time and grease or oil in some cases, it can also induce harm. And this is especially true for electric motors where over-lubrication often leads to grease getting into the motor windings and causing a failure. Precision lubrication really requires a holistic approach. It requires that we do a lot of things right. We have to get the correct lubricant specified. That's probably the first thing that we need to do correctly, is have the right oil or right grease in each application. We also need a good education program. We need to make sure that technicians, that engineers, that the folks who are designing, implementing, or executing and managing the lubrication program understand not only the fundamentals of lubrication, things like lubricant selection, but also that they understand the implications of their actions. They need to understand the implications of adding the wrong grease or contaminating lubricants, etc. We also need to optimize PMs. We need to make sure that all lubrication tasks are done at the most correct time and that they're done in the most correct way. We need good contamination control. Even if we have the right oil in each application, if the oil's heavily contaminated, we're going to have excessive wear. In fact, lubricant contamination is the #1 root cause of wear in lubricated machinery. Good lubricant storage and handling is really the foundation of contamination control. So it's going to be an important part of any precision lubrication program. And finally, we need a good oil analysis program to verify that the lubrication activities that we're doing are being effective. We need to verify that we do in fact have the correct lubricant in each application and that it's there in the correct amount and that it is in suitable condition, chemically speaking, performance-wise, and certainly that it's suitably free of contaminants. Now the good news here is that doing lubrication the right way, the better way, is typically easier than doing it the way most people do it or the way things have been done traditionally. And electric motors are no exception. For electric motor lubrication, doing things the right way usually means doing a lot less of it. So precision lubrication for electric motors has 4 components. Product selection. We need to select the correct grease. We need to identify the correct amount of grease that's applied with each application, and we need to determine the frequency with which it should be applied. And lastly, we need to have a good, correct, and consistent procedure for applying that grease. So no matter who is executing this lubrication activity, it's going to be done to a certain standard. So let's focus on the first aspect. Let's focus on product selection. Now, for electric motors, this is really easy because most lubricant manufacturers make a product that's called electric motor grease, or at least it's identified as being appropriate for electric motors. But the same grease, the same parameters apply to other high-speed bearings, not just electric motors. So it's a good idea to understand not only which grease should go in the electric motor, but why. Why is that grease appropriate for electric motors? Most people misunderstand grease. They think of grease in terms of the type of thickener it uses. So they think of it as polyurea grease. In fact, if you ask a lot of folks what type of grease you should use in an electric motor, they'll say polyurea grease. Well, that's the thickener type. It doesn't actually say anything about the lubricating oil. The thickener doesn't actually lubricate anything. All it does is holds the lubricant in place. So a grease is a lubricating oil just like any other oil that we would use, like EP220 gear oil or ISO 68 anti-wear oil, that's had another component added to it, a thickening agent that allows it to stay in place. It allows it to stick to things. So when we select our grease, we need to think about it in that way. We need to first consider what type of oil we would use in that application, and then we can think about the other grease attributes such as thickener type, NLGI grade, and so on. The most important property of any lubricant, whether it's oil or grease, is the viscosity of the base oil. So that's the first thing that we need to get right. It's the most important thing to get right. When we're selecting a lubricating oil, we really look at two things. We look at the base oil and its viscosity, and then we also look at the type of lubricating oil or the type of additive system that it uses. In the case of grease, we'll usually focus on EP or non-EP. Now, in the case of electric motors, we're typically going to go with the non-EP. It's usually going to be an anti-wear type of oil. Once we figured out what type of oil to use, viscosity grade and oil type, then we should look at what type of thickener is most appropriate and what NLGI grade or consistency is most appropriate. Now, you could use a number of different thickener types for electric motor grease, but polyurea or lithium complex both have properties that make them suitable for electric motor lubrication. Again, the most important thing to focus on is viscosity. So we're going to look at the actual process that we can use for identifying the most appropriate viscosity for not just an electric motor bearing, but any anti-friction or element bearing. The first step in the process is to identify what we call the minimum operating viscosity. That is the actual viscosity of the oil at the operating temperature that is required to create a thick enough oil film to prevent metal-to-metal contact or to overcome the surface roughness of the interacting surfaces. So we can use the chart you see on the screen here to do that. And in this chart we need to know two things. We need to know the dimensions of the bearing, and we need to know the rotational speed. So on the x-axis at the bottom here, we see the mean diameter, or sometimes called pitch diameter, of the bearing, and then we have these diagonal lines that represent different rotational speeds. So we need to calculate the mean diameter of the bearing, which is simply the outside diameter plus the inside diameter divided by 2. So let's just, as an example, assume that our electric motor has a mean diameter, the bearings have a mean diameter of 100 millimeters. So we go down to the x-axis, come up from 100 millimeters to the most appropriate rotational speed. Let's just assume again that our electric motor is an 1800 RPM motor, so that's pretty close to 2000. So we'll just come up to the 2000 line. The next thing we do is move over to the y-axis, and we can read from the y-axis the minimum required operating viscosity. So in this case, it's going to be about 8 centistokes. So 8 centistokes is the viscosity that is required to give us a full viscosity oil film in our application. Now, like with most things, we don't want to use the bare minimum. We're going to use some multiple of that, where we want some extra viscosity to give us a bit thicker oil film. How much more we use depends on several things. This multiple of minimum viscosity is referred to as the kappa value. The kappa value is simply the ratio of the actual viscosity of our oil to the minimum required viscosity of the oil. So for slow speed bearings, a lot of times we'll have a kappa value of less than 1, which means we do have or will have metal-to-metal contact. The reason for this is that with slow speeds, it's not as important to have a thick oil film, but also it's just impractical in a lot of cases, because to use that much viscosity would require additional lubricants and inventory, etc. For high-speed bearings such as those in an electric motor, we typically want to use a good bit more than the minimum. So if we use a kappa value of 1, that would be the bare minimum. That would be our minimum value of 8. If we use a kappa value of 2, that would be 16. Optimum bearing life is achieved when we have a kappa value of 4. Now there are reasons we would want to use a little less. There are reasons we might want to use a little more. With oil lubricated bearings, especially if we have good contamination control and consistent temperatures, we might want to get closer to 1, maybe 1.5 or 2. But with grease lubricated bearings where we don't have very much control over contamination and operating temperatures can fluctuate a good bit, we usually use a little more. So in this case, let's just assume that we've decided on a kappa value of 4. Say that is most appropriate for our particular motor bearing. So if we take our minimum viscosity of 8 and we multiply that by our kappa value of 4, that's going to give us a target or an optimum viscosity of 32 centistokes. So our next step is to figure out what viscosity grade will give us 32 centistokes at our operating conditions. Operating conditions in this case really means operating temperature. Now we don't necessarily know the operating temperature of every electric motor. Moreover, if we were to go out and measure the operating temperatures, they can change from day to day depending upon the ambient environment. So we want to focus on the higher end of what we think the temperature might be. So let's look at the highest likely operating temperature. And in our case, let's just say that we've assumed that to be 75 degrees C. So 32 centistokes is our target. We want to pick a viscosity grade that's going to give us 32 centistokes at our target temperature, or at our highest likely operating temperature. So if you look at all the different lines on the chart here, each one of those lines represents a common viscosity grade. So they start at 22 and go up to 1,000. So this is going to tell us the kinematic viscosity in centistokes at each of these temperatures. So again, we've identified a highest likely operating temperature of 75 degrees C. So if we look at where these two lines intersect, that should be our target viscosity grade. And as it turns out, these lines intersect right on top of the orange line, which is an ISO 100. Now that's very convenient because most electric motor greases have a base oil viscosity of about 100 centistokes at 40 degrees C, or an ISO viscosity grade of 100. So that's not only going to be appropriate for electric motors, that's going to be appropriate for any bearing that's operating under similar conditions. So assuming that we are going to use an ISO 100, we need to determine what type of oil we should use. And in this case, we're going to use an anti-wear oil. We don't need EP additives for high-speed bearings, so we want to use an AW100. The only two other things we need to do is to determine what type of thickener and what NLGI grade. Well, for electric motors, we're usually going to use polyurea or lithium complex. Either one of those will work just fine, and you could use others. Those are just suggestions. The appropriate NLGI grade for most manually lubricated bearings is going to be NLGI2. So we want a polyurea or lithium complex NLGI2 with a base oil viscosity of 100 and with an anti-wear additive system. And that is our lubricant specification. Again, electric motor grease, if we choose something that's identified as such, will typically conform to those specifications. But we shouldn't use general purpose grease or multi-purpose grease or anything else. It should be a grease that conforms to approximately these specifications. So now that we've decided what kind of grease we're going to put into our motor bearings, we need to figure out how much should be in the motor bearings. And there's really two answers to that. There's how much we should put in there initially, and then there's how much we need to apply when we replenish that grease. We want to start out with not the ideal amount of grease, but we really want to start out with as much grease as we can put in there without causing any harm. For very slow speed bearings, this means filling the bearing housing completely full. For higher speeds, we want less grease because the faster it turns, the more that extra grease is going to harm us. It's going to take more energy to push through that grease, and it's going to end up it's going to result in elevated operating temperatures. So the faster it goes, the less grease as a percentage of the volume we want to use. So most electric motor bearings are going to fit into the range of speed factors that are in the middle here, 50,000 to 200,000. So what that means is if we have an open bearing or a single shielded bearing, we should initially pack that bearing completely full, and then we should leave the space around it empty to some extent. So we want to fill the space around it, in this case 50 to 75% full. So when that machine starts up, the extra grease that's in that bearing will have some place to go. It'll get slung out, and it'll basically kind of come to equilibrium. It'll kind of find where it wants to be in terms of how much grease is retained inside the bearing. Now for double shielded bearings, it's much more difficult, if not impossible, for that grease to get out. So in that case, we want to start out with the ideal amount of grease inside the bearing, which would be about a third full. And then the space around the bearing we want to fill to the same specifications, about 50 to 70% full. Now there's two other considerations for initial fill, and one is in a lot of electric motors we have to use an extension on the fill port in order to get access to it because of coupling guards and things. So when we install that extension, we want to make sure that we pre-fill that with grease so that when we replenish grease, that's not going to be a factor. It's going to automatically start applying that amount of grease. Otherwise, it might take several applications to actually fill that pipe extension. So we want to make sure we start out with that full. And then if we use an extension on the relief fitting on that electric motor, we want to make sure that that is empty. Now, even with doing that, there's a decent chance that the grease that makes its way into that tube is going to harden over time and cause problems. But by leaving it empty to start with, we're going to have the best chance of it actually working properly going forward. So that's the initial fill, and that's easy. The thing that we're going to do much more often is figure out how much we apply ongoing when we replenish that grease. Over time, the grease in that initial fill is going to get, in some sense, worn out. So the oil is going to separate from the thickener, some of it's going to evaporate, some of it's going to run out, and the grease is going to start to become dry. As that happens, our lubricating film will start to dissipate. So we need to replenish that grease from time to time, and the amount that we use in most cases is just going to be a function of the size of the bearing. So we take the outside diameter of the bearing in millimeters and multiply that times the width of the bearing in millimeters, multiply that times 0.005, and that is going to give us the appropriate replenishment volume in grams. Now, of course, we can use different dimensions. We can use inches, and we can multiply those times 0.114, and that's going to give us the appropriate replenishment amount in ounces. So again, this is pretty straightforward. It's pretty simple stuff. We start out with this amount. This is the amount that we apply when we replenish the grease. The tricky part is really determining how often we should apply it, because there's a lot of factors that go into that. But for electric motors, it's pretty straightforward. But this is just one of the methods, and this one on the chart here, this comes from SKF. And this is one method that we can use to determine how often or when we should reapply the grease. So we're going to have to calculate a few things. If you look at the x-axis on the chart here, you'll see A times BF. Well, that A is the NDM speed factor. So to calculate the NDM speed factor, we multiply the rotational speed times the mean diameter. We'll go back to our original example and use 100 millimeters as our mean diameter, and we multiply that by our rotational speed of 1800 RPMs, and that gives us 180,000. That's our NDM speed factor. Now notice there's one other factor there. There's the bearing factor, or B sub F. That is an adjustment or a correction for the type of bearing that is used. Different bearings allow grease to last different lengths of time or different service lives. So ball bearings, grease in a ball bearing has a very long service life. Grease that's in a spherical roller bearing has a much shorter life, or a tapered roller bearing. And this has to do with the amount of contact. Basically, the contacts in the bearing squeeze the oil. out of the grease. And so the more contact there is, the more of this effect we're going to get. So with ball bearings, again, we have a very long grease life, so that gets a factor of 1. If it was a cylindrical roller bearing, as some motors do have, we'd use a factor of 1.5. So in this case, it's not going to change the value on the x-axis. It's 1800 times the mean diameter of 100 times a bearing factor of 1 gives us 180,000. So we go down to the x-axis and we follow the line from 180,000 up to the line that reflects the appropriate load ratio. In this case, we'll assume that the load ratio is approximately 8. So that's the middle line. So if we go up to the middle line to 8 from 180,000, and then we track over to the y-axis, this is going to give us our recommended relubrication interval in operating hours. So in this case, we've arrived at 6,000 hours, or about 8 months. Now, 8 months, to me, is not really a convenient task frequency for lubrication PMs. So what I would do is adjust that. I'd probably adjust that down to 6 months, and I'd use a little bit less grease. In this case, I'd use about 3/4 of the specified amount of grease, or the one that we determined from the equation, and I do it every 6 months. Or I could change that to 9 months and use a little bit more grease. As long as we have the same application rate, we should still be fine. Most of these, or really all of these recommendations, whether it's OEM recommendations or bearing manufacturer methods like the one we're looking at here, these are only approximations. There are so many factors involved that it's impossible to be truly precise in terms of calculating the appropriate amount of grease or relubrication frequency or rate. So anything in the right ballpark is going to be appropriate. Now we can make some adjustments to that. We should look at that value as the starting point, or the default value. We may want to make adjustments to that based on certain operating conditions like temperature. Some of these things we can quantify, some of them are a little more subjective, things like moisture and particle contamination. And those really aren't going to apply so much when it comes to electric motors. At least hopefully we don't have too much particle and moisture contamination in our electric motor bearings. So let's focus on the ones that we actually can quantify. For temperature, we want to reduce the interval by half for every 25 degrees Fahrenheit above 150. So if we said 6 months, if we were operating at 175 degrees, we'd want to do the same thing every 3 months. Some of the other things that we can quantify are things like the orientation of the bearing. If this motor happens to be vertical, we want to lubricate that twice as often as well. So any bearing that's on a vertical shaft needs to be greased twice as often as one on a horizontal shaft. And then also vibration. The higher the vibration, the faster the grease separation, the faster the grease gets used up or consumed. So if you want to put a number on it, for every 0.2 inches per second, we want to reduce our interval by 1/3. Now, the method that we just went through, including the correction factors, that really works for most grease lubricated bearings. But for electric motors, a lot of times we can take a simpler approach, and sometimes even a better approach, is to look at the equipment manufacturer's recommendations. All electric motor manufacturers specify recommendations, or they publish recommendations for grease volume and grease application frequency. The one we see here is one example of that. And in this case, we really don't need to collect very much information in order to make these determinations. We simply need to know the frame size of the motor, the rotational speed, and we also need to be able to characterize the service condition as standard, severe, or extreme. And in the recommendations, this OEM is going to make a much clearer explanation of standard, severe, and extreme. But just to put it in the simplest terms, standard would be like 8 hours a day, 1 shift per day. Severe would be 24/7, and extreme would be 24/7 with high vibration, high temperatures, etc. So it's kind of hard to put a fine point on it, but again, these are just approximations. So as long as we're in the right range, we should be good. So for grease relubrication frequency, if the motor's, depending upon the motor size, is going to be somewhere from 1 month to 12 months. That's a pretty big range. But if it's a large motor, 404 to 449, it's going to be probably 6 or 3 months, depending upon the conditions. And the same conditions are going to apply to most equipment in the plant. Usually one machine is going to be subjected to the same kind of environmental conditions as most of the others. For those 254 through 365, we're going to be 3 months to 12 months, depending upon the service conditions, and for the smaller ones, 6 months to 12 months. But it wouldn't be too much of a stretch to really kind of fit all of these, kind of shoehorn these into a couple of different categories, and then just make minor adjustments. So, we could do a certain set of motors that's every 3 months, some that are 6 months, some that are 9 months, and some that are 12 months. And then we can use the frame size to estimate the amount of grease as well, because motors of the same frame size are going to have the same approximate bearing sizes. So if we have a motor that's in the range of 324 to 365 frame size, it's going to get 1.5 cubic inches of grease. Now, if you look at 3 different methods to make these determinations, you're probably going to get 3 different answers, but again, they're going to be in the same ballpark. One of the things that we would recommend is that you use a consistent source. So, even though you get 3 different answers, it's hard to say whose is better. But what you should do is make sure you use the same source to determine the amount of grease that you do to determine the frequency, because it's the rate of application that really matters. Now, we're not quite done. Once we've determined the amount of grease that goes in and how often we need to apply it, when it comes to actually developing lubrication PMs, we need to be able to express this. We need to be able to communicate this to the technician in terms that are easy to interpret. And if you're standing out in the plant holding a grease gun and you have a PM sheet that says apply 17 grams of grease, not everybody knows exactly how to get 17 grams of grease out of any grease gun. We usually want to describe grease amounts in terms of shots. It's 7 shots, or it's 10 shots, or it's 5 shots. But we really need to define what a shot is, because different grease guns can, they can have different answers to that question. Grease guns can range anywhere from 5 shots per ounce to 45 shots per ounce, or even higher, depending upon the type and the make and model. So, there's no magic solution for this, but we are going to have to address it in some way. And there's really 3 different ways to go about it. We could either use a standard type of grease gun for the whole plant. So everybody uses the same make and model of grease gun. It's got a known output ratio, ounces per strokes or whatever. And we can using that knowledge, we can specify how many shots of grease for each application. That's not practical for everybody. We could take each grease gun and weigh out a shot of grease and see how many shots it takes to make a gram or a cubic inch or an ounce or whatever the units are that you want to use. And that can be somewhat challenging because we have to do a little math along the way. Or we could simply use a meter attached to the grease gun that tells us exactly how much grease comes out. Obviously, this is the better choice in terms of accuracy and reliability. This is going to take all the guesswork out. So that would be our standard recommendation. So now that we've decided what grease we're going to use, how much, how often we're going to apply it, and how we're going to communicate that, we need to decide what the most appropriate method is for applying that grease. And there's no one right way. Some of these things are optional. We may or may not want to do all of the things in the procedure listed here. Like the first step. Okay, the first step in this procedure is to remove the vent plug. There are advantages to doing this, but there are a lot of cases where it's not possible because it's inaccessible, or it may just be impractical. It may be inconvenient to remove the vent plug from a motor bearing. If we add the correct amount of grease at the correct frequency, there should be no significant need to purge old grease from the bearing. If we use the right amount at the right frequency, it should take many, many years before old grease becomes a problem in the bearing. So this notion of purging electric motor bearings, in my opinion, is way overrated and not necessary if everything else is done correctly. Nonetheless, it is helpful to do. It is a best practice. So when we can do it, when it is convenient to do it, it's a good idea. So in the case of our procedure here, we're going to go ahead and remove the vent plug if we can. Now the next step is not really optional, and that is to wipe the grease fitting. That is really the extent of our ability to control contamination in a lot of grease lubricated components, is simply to wipe the grease fitting and then purge a bit of grease from the grease gun nozzle and wipe the nozzle as well. That's as much as we can do, and there's no reason not to do it. The next thing we want to do is to carefully apply the requisite amount of grease. Now that amount of grease that we determined either from OEM recommendations or from a calculation, we should view that as a maximum amount of grease, especially if we're removing a vent plug. We want to apply grease until grease is relieved from that vent, or we achieve that calculated amount of grease or that specified amount of grease. We do not want to exceed that. So that should be viewed as the not to exceed amount of grease. We don't have to add more if we have grease being expelled from the vent. Likewise, and even more importantly, if we have back pressure on the grease gun, if at any point we're adding grease and we start to feel more pressure being applied at the grease gun, we want to stop, because that means something is wrong. There's an obstruction that's preventing grease from getting where we want it to go, or the bearing housing is completely filled with grease and we're just pressurizing it. So if we do that, it is also a good idea to remove the fill fitting, remove the Zerk fitting, and allow that excess grease to escape, give that pressure somewhere to go. So once we've either applied grease until it comes out, or we've reached that maximum amount of grease, the last thing we want to do is leave some grease on the fitting. This accomplishes several things. It protects the grease fitting from corrosion and other harm. It also makes it easy to clean the next time we come through to add grease, and it also shows us what kind of grease went into that application last time. So if we're approaching a bearing and we're going to apply blue grease to it and there's red grease on the grease fitting, that's going to give us pause and cause us to investigate and find out what the problem is. And as the actual last step here, if you did remove the vent plug from the bearing housing, you want to wait 10 to 20 minutes before you replace it. A lot of times when we add grease and we've removed the vent plug, no grease comes out initially, but if you wait 10 or 15 or 20 minutes, some of that grease does come out once it gets warmed up and starts to move around in there. So it's a good practice to wait 10 to 20 minutes before replacing that plug. And you can go on and do other activities, such as grease the next few motors before you return to replace those. So essentially, that is precision lubrication for electric motors. It's a huge opportunity for most plants. It's something that, quite frankly, most people don't get right, at least initially, but it can be simplified if we do those four things. And we need to use a valid approach, some type of recognized authority for how we make those determinations. So we need to select the correct grease. We can do this by following standard methods like we discussed, or you can go to the equipment manufacturer or your lubricant supplier for a recommendation. Then we need to determine the most correct amount and frequency. Again, there's multiple sources for that one, as long as we're not just guessing at it. Okay, all we need to do is get in the right ballpark. It doesn't need to be exact. And then finally, we need to have a good, a correct, and a consistent application procedure that we can train on so that all technicians are applying grease in the same way every time. This way we can begin to measure the effects of precision lubrication on not just electric motors, but our other grease lubricated bearings as well. This has been Precision Lubrication for Electric Motors. I'm Jared Pottiger, Education Services Manager for Deskcase.